really sneak up on you.
You do it in the real class too. Don't worry, that's just convoluted.
It's like, I looked at my comm class this week, but I should probably do that because I have a speech coming up.
You know, they had an online part portion before COVID. And for that, they would actually have to find an audience of at least like 3 people, like family members or friends.
They recommended that we do it in front of people, but I don't know that many people, so.
See, I'm not a particularly social person, but when I'm giving a speech, I feed off of the feedback that they give me.
So what made me most annoyed though is that they were like, you have to do it in front of a plain wall, and I was like, okay, well, I live in a dorm room, so you're gonna see my dorm room. Congratulations. This isn't very plain, but that's all I have.
You have to find that's empty for that. Well,
And I'll do that. It can help that I was recording the last minute. You know. Still wasn't great as well.
last semester I did have to give one speech.
We'll start in about a minute.
It was a little bit, it was okay, because it was this spring, so everybody had already been in the class and what we were expected. Yeah. It's really weird though, because some people had already grown beards.
Today we'll be in section 10.4. The topics are areas and arc lengths in polar coordinates. First, we will review how to find the area of a sector of a circle. So if we have a circle with radius r, and then if we carve out a sector with central angle theta radians, first the area of the circle we know that that's pi times the radius squared, and so the area of the sector with central angle theta radians I'll refer to that as a sub theta. So do you remember what that's equal to? The area of the sector is just a fraction of the area of the circle. What fraction is it? Well, it's, yeah, theta over 2 pi times the area of the circle. Theta over 2 pi represents what fraction of the entire circle we're trying to find the area of. The pi units cancel. The number pi divided by pi is 1. And we usually see this written as 1/2 r squared times theta. Okay, we're going to use that idea of the area of a sector of a circle to derive a formula for finding the area bounded by a polar curve, r equals f of theta, between the rays, theta equals A and theta equals B. Okay, so if we have some polar curve, let's call it R equals f of theta. And a polar axis. So this point is the origin, capital O. And if we look at a portion of the polar region between theta equals A and theta equals B, we want to find a formula for the area of this polar region. So this polar region is bounded by the polar curve R equals f of theta and the rays theta equals A and theta equals B. So just like we always do, or usually do in cases like this, we're going to subdivide this angle between theta equals A and theta equals B. Think about subdividing that into n subangles emanating from the origin. But we're going to just focus on one of those. One of those subangles, and we'll refer to the central angle as delta theta. It might be better if I draw a bigger picture of the subangle that we're looking at. So that we don't have to squint. So this is delta theta. It's one of the n sub angles. And I'll refer to this ray as theta equals theta sub I minus 1, and the other ray as theta equals theta sub I. And this is part of the polar curve, R equals f of theta. Okay, so for a particular theta value between theta sub I minus 1 and theta sub I, we use that as the radius of a sector of a circle. So we will refer to that as f of theta sub I star. Okay, so do you see what's going on? This is supposed to be the sector of a circle with radius f of theta sub I star. It's just a point on the polar curve for a particular value of theta. And if we refer to the area of that region as a sub I, then we can approximate that region of the polar curve using the area of the sector of the circle. Okay, so the central angle is delta theta, so the area of the polar region is approximately equal to 1/2 times the radius squared. The radius is f of theta sub I star, multiplied by the central angle d theta. All we did was use the formula for the area of a sector of a circle. Okay, we do that for each of the n subregions. This is just representing one of the n subregions. And so the total area, so the area bounded by r equals f of theta, and the rays theta equals a and theta equals b. This can be approximated by a Riemann sum, each of the terms having this form. So the sum from I equals 1 to n of 1/2 times the square of f of theta sub I star times delta theta. And then if we take the limit, let n go to infinity, we're going to get a definite integral for the area of the entire region bounded by the polar curve in the rays theta equals a and theta equals b. Okay, so we'll write down the definite integral for the area. It's the definite integral from theta equals a to b of 1/2 times the square of f of theta d theta. Okay, that's our formula for finding the area of a region bounded by a polar curve between two rays, theta equals a and theta equals b. Okay, what we'll do next, we'll look at a few problems. To start with, we'll just set them up, and then as time permits, we'll go back and evaluate them. But once we get them set up, they aren't that hard to evaluate. But we have to be a little bit careful when setting them up. This one says, find the area inside the polar curve, r equals 3 times cosine of theta. So this just means that f of theta is 3 times cosine of theta. You can use these equivalent formulas. This is the one that we just wrote down a few seconds ago. The definite integral of 1/2 times the square of f of theta from theta equals a to theta equals b, or you can write it this way, the definite integral of 1/2 r to the second d theta from theta equals a to theta equals b, since r equals f of theta. Okay, so for this one, we need to determine what the limits of integration are going to be. We've seen this curve before, I think. So why don't we get a sketch of it first by graphing this in the Cartesian plane for r and theta. So the graph looks something like this. So this is pi over 2, pi, 3 pi over 2, and 2 pi. And it ranges from -3 to +3. Okay, so when we sketch this polar curve, r equals 3 times cosine of theta, what are we going to get? Well, we do it one portion at a time. So when theta is 0 degrees, we're looking at the horizontal to the right. The r value is 3. That's not r to the third, that's 3. So we have this point on the graph. When theta equals pi over 2, we're to the positive vertical axis, and the r value is 0. And in between, we're going to get, turns out to be a half circle. Between pi over 2 and pi, so those are the angles from the third quadrant to the fourth. The r values are negative. So what's going to happen for the polar curve? Yes, so yes, between pi over 2 and pi, the r values are negative, so they'll be in the opposite side of the origin. So we'll get the other half circle. So when we're at pi, that's here, but the r value is negative 3, so the point is plotted 3 units in the opposite direction. And then between pi and 2 pi, the circle is just retraced again. We only want one tracing of the circle to find the area inside that circle. So our limits of integration are going to be from 0 to pi, because we traced out the circle from 0 to pi. You see what I mean? Okay, so the area, we already know what the area of a circle is, but it's the definite integral from 0 to pi of 1/2 times r squared. R is 3 times cosine of theta. So we'll do a little bit more right now. We get 1/2, and then when we square 3 times cosine of theta, we'll get 9 times cosine of theta squared. And we can come back and evaluate this if we have time a little bit later, but we've evaluated integrals like this before. So before moving on, how are we going to deal with the integral of cosine of theta squared? So I'll just remind you the way that I'm going to do it. I remember that cosine of theta squared is 1/2 plus 1/2 times cosine of 2 theta. Okay, let's set up the next problem. Find the area inside the polar curve r equals 3 plus 2 times sine of theta. Well, we know that we're going to square this, multiply it by 1/2, and compute a definite integral. But what will the limits of the integral be? That's the question we have to answer before we go about trying to find the area that's inside the polar curve. Well, usually what I have to do is I usually have to sketch the graph of the polar curve, and then I'll be able to figure out what the limits of integration have to be. So we can do that here on the side. So since we just have a sine of theta, we know that we need to consider what happens between 0 and 2 pi. So we'll try that out. Okay, so when theta is 0, the r value is 3. When theta is pi over 2, sine of pi over 2 is 1, and 3 plus 2 is 5. When theta is pi, 2 times sine of pi is 0, so we're back at 3 again. And 3 pi over 2, sine of 3 pi over 2 is negative 1. 3 plus 2 times negative 1 is 1. And then when theta is 2 pi, r is 3 again. So in the Cartesian plane, we get this graph. And then the polar curve, what's it going to look like? I always do something to, oh well. Okay, so when theta is 0, the r value is 3. When theta is pi over 2, the r value is 5. So the positive vertical axis corresponds to pi over 2. So we're up here at 5. And when theta equals pi, the r value is 3. So we're over here at 3, negative 3, I should say. And then at 3 pi over 2, the r value is 1. So we're just down to that point. And then from 3 pi over 2 to 2 pi, the curve goes back to 3. So this is roughly what the curve looks like. Roughly speaking. But the information that we were after is that it took us between 0 and 2 pi to sketch the curve. So that means the limits of the integral have to be from 0 to 2 pi. Okay, so the area that's enclosed is the definite integral from 0 to 2 pi of 1/2 times the square of 3 plus 2 sine of theta. Okay, we'll take it a couple of steps further before moving on. When we square the quantity 3 plus 2 times sine of theta, we'll get 9 plus 12 sine of theta plus 4 times sine of theta squared. So we know how to find antiderivatives of constants and sine of theta, but how are we going to deal with sine of theta squared? So sine of theta squared, well, the identity I like to use is 1/2 minus 1/2 cosine of 2 theta. Okay, let's look at the next problem. Set it up. So this one, find the area inside the curve r equals 3 times cosine of theta, and outside the curve r equals 1 plus cosine of theta. R equals 3 times cosine of theta. We already graphed that once today. So I'll just regraph that since we know what it looks like. So the polar curve, anyway, is a circle. So that is r equals 3 times cosine of theta. Then what does the graph of r equals 1 plus cosine of theta look like? Well, if we first draw this in Cartesian coordinates, then we can sketch the graph along with this one. So r equals 1 plus cosine of theta. We'll see what it does between 0 and 2 pi. Theta and r. So when theta is 0, r is 2. When theta is pi over 2, 1 plus cosine of pi over 2 is 1 plus 0, or 1. So let's see, when theta is pi, cosine of pi is -1. 1 plus -1 is 0. 3 pi over 2, cosine of 3 pi over 2 is 0, so we're back to 1. And then cosine of 2 pi is 1, 1 plus 1 is 2. So this is the graph, roughly. Okay, so let's sketch that over here, the polar curve. So when theta is 0, the r value is 2. At pi over 2, the r value is 1, so the polar curve gets to this point. It has to intersect the circle somewhere. And then at pi, the r value is 0, so it goes here. Then between pi and 3 pi over 2, at 3 pi over 2, the r value is 1, so it's down here. And then at 2 pi, it's back to 2. Okay, so that's not the greatest graph, but it might help us. We want to find the area inside the circle, but outside the cardioid. So I'll color that using this green pen. We want to find that area. So how are we going to find the limits of integration? So there's a ray that intersects where the two polar curves intersect at both of those points. So we need to find the theta value at those two intersections. So how are we going to do that? Well, the concept is not new. We want to find where these two curves intersect. So we set them equal to each other and solve for theta. So we set 3 times cosine of theta equal to 1 plus cosine of theta. And if we subtract cosine of theta from both sides, we get 2 times cosine of theta equals 1. Divide both sides by 2. Cosine of theta is 1/2. And cosine of theta is 1/2 when, well, in our picture, we want theta to be negative pi over 3 and pi over 3. Cosine is positive in the 4th quadrant, so this angle is negative pi over 3. And in the 1st quadrant, theta is pi over 3. Okay, so those are going to be the limits of integration. So the area that's inside the circle but outside the cardioid is the definite integral from negative pi over 3 to pi over 3 of 1/2 times. Okay, so we're going to square 3 times cosine of theta. And from it, we're going to subtract the square of 1 plus cosine of theta. Okay, so that's the basic setup for that one. We can take it a little bit further right now. So 1/2 times all of this. So when we square 3 times cosine of theta, we get 9 times cosine of theta squared. And then we're subtracting the quantity 1 plus cosine of theta squared. So we'll do a little bit of it in our heads. We have to subtract 1. We also have to subtract 2 times cosine of theta and subtract cosine of theta squared. Okay, so we can simplify this integrand more. We'll end up with 8 times cosine of theta squared minus 1 minus 2 times cosine of theta. And then when we compute the integral, we have to replace cosine of theta squared with 1/2 plus 1/2 cosine of 2 theta again. Okay, but this is the setup for that one. Okay, on the next one, let's find the area of one loop of the polar curve r equals 2 times sine of 3 theta. So how many loops will this polar curve have? yeah, it's going to have 3. When you have sine of some positive integer times theta, if the positive integer is odd, then that will be the number of loops. So the graph of this will have 3 loops. On the other hand, if the integer is even, like yesterday we did something involving sine of 4 theta, that had 8 loops. So when the integer is even, you have twice as many loops as that integer. So this one will have 3. We just want to find the area of one loop. So I'll go ahead and sketch the graph of the Cartesian graph for r equals 2 times sine of 3 theta. So 0 is less than or equal to 3 theta, which is less than or equal to 2 pi. So that means one period of this will be between 0 and 2 pi over 3. So if we divide the interval from 0 to 2 pi over 3 into 4 equal subintervals, then each subinterval will be of length pi over 6. So I'll mark those off. Pi over 6, 2 pi over 6, which is just pi over 3. 3 pi over 6 is pi over 2. And 4 pi over 6 is 2 pi over 3. So I'll get one period of this graph between 0 and 2 pi over 3. So one period. So I'm using this so that I can find an interval to integrate so that I can find the area of one loop. So let's sketch the polar curve. And the intervals, the subintervals are of 30 degrees or pi over 6 radians. So I'll mark off, subdividing that into intervals of pi over 6. So in the polar curve, when theta is 0, r is 0. When theta is pi over 6, the r value is 2, so it's 2 units from the origin along pi over 6. And then between pi over 6 and pi over 3, we complete one loop because the r value is back to 0 at pi over 3. So what can I use for the limits of integration if I want to find the area of just one of those loops? We sketched one loop between 0 and pi over 3, right? So between 0 and pi over 3, between theta equals 0 and theta equals pi over 3, we were able to sketch the graph of one loop. So to find the area of one loop, we compute the definite integral from 0 to pi over 3. And the integrand is 1/2 times r squared, where r is 2 times sine of 3 theta squared. Let's take it just one step further for now. The integral, definite integral from 0 to pi over 3. 1/2, when we square 2 times sine of 3 theta, we're going to get 4 times sine of 3 theta squared. 1/2 times 4 is 2. So I'll write it as 2 times sine of 3 theta squared. Okay, what should we use in the next step in order to integrate sine of 3 theta squared? Well, the way I'm going to do it is I'm going to replace sine of 3 theta squared with one half minus 1/2 of cosine of 6 theta. Same idea as we saw earlier, just with a different argument. Okay, that's a pretty good setup for that one. Let's move on to arc length. To find the length of a polar curve, r equals f of theta, for values of theta between a and b, we regard theta as a parameter and write the parametric equations for the curve the way that we have been. X equals r cosine of theta equals f of theta times cosine of theta, and y equals r sine of theta, or f of theta times sine of theta. Now we differentiate x and y with respect to theta so that we can find the square of the derivative of x with respect to theta plus the square of the derivative of y with respect to theta. So why is that going to be of interest when we're interested in arc length? Well, you'll see soon enough. So let's find this. First, we want to know what dx d theta is before we square it. We've already seen this a couple of times. Remember that r is a function of theta, so we use the product rule. The derivative of x with respect to theta is the derivative of r with respect to theta times cosine of theta. And then it's plus r times the derivative of cosine of theta, which is negative sine of theta. So we'll just go ahead and write minus r times sine of theta. And then find the derivative of y with respect to theta. So y is r times sine of theta, and r is a function of theta. So the product rule again. We have the derivative of r with respect to theta times sine of theta, and then plus r times cosine of theta. Now we want to square each of those and add them. So it might be better if I just square each one first. So let's square dx d theta. We're going to get dr d theta squared times cosine of theta squared. And then we're going to get minus 2 times r times dr d theta times cosine of theta sine of theta. And then we're going to get plus r squared times sine of theta squared. Now we will square dy d theta. When we square dy d theta, we'll get dr d theta squared times sine of theta, and then plus 2 times r times dr d theta times sine of theta cosine of theta, and then plus r squared cosine squared of theta. I should have said cosine of theta squared. Then when we add dx d theta squared to dy d theta squared, we'll get we'll get some cancellations here. Let's see, I need to square this sine of theta, right? Because when we're squaring dy d theta, we're squaring this term. I squared the dr d theta, but I failed to square sine of theta the first time. Okay, so I think we're okay now. Notice that the 2 middle terms add up to 0. So we can eliminate those. And what do we get when we add dr d theta squared times cosine of theta squared, when we add that to dr d theta squared times sine of theta squared? Okay, we're going to add these terms. I'll go ahead and write part of it down. I'm going to factor dr d theta squared out of the sum. I'm adding these terms, and then I factor out dr d theta squared. I'm left with cosine of theta squared plus sine of theta squared. And we know that that's equal to 1. Yeah. And then a similar type of thing is going to happen over here when we add r squared times sine of theta squared to r squared times cosine of theta squared. If we factor out r squared inside the parentheses, we just have sine of theta squared plus cosine of theta squared. So this simplifies to dr d theta squared plus r squared. Sort of nice how it turns out. Okay, well, remember from section 10.2, if we replace t with theta, the arc length for r equals f of theta for values of theta between a and b, the arc length formula is the definite integral from a to b of the square root of dx d theta squared plus dy d theta squared. We just derived what dx d theta squared plus dy d theta squared is. That's dr d theta squared plus r squared. Then the arc length formula for a polar curve is the definite integral from theta equals a to theta equals b of the square root of dr d theta squared plus r squared d theta. We'll start working on the first arc length problem. Uh, This one says find the arc length of the curve. R equals 1 minus sine of theta. So we need to know what the limits of integration are. Well, it's just a curve. Let's just go, well, I don't know, maybe it will double back on itself. Who knows? So let's sketch it in the Cartesian plane first. So when theta is 0, we're at 1, r is 1. At pi over 2, sine of pi over 2 is 1. 1 minus 1 is 0. Sine of pi is 0, so 1 minus 0 is 1. At 3 pi over 2, sine of 3 pi over 2 is negative 1, so 1 minus negative 1 is 2. So it's up here, and then 2 pi, we're back at 1. So the graph looks something like this. So the polar curve when theta is 0, r is 1. When theta is pi over 2, r is 0. When theta is pi, r is 1 again. So we're doing something like this. At 3 pi over 2, r is 2. And then at 2 pi, r is 1 again. So it looks like, obviously, we need to go from 0 to 2 pi. We're out of time, but just use the arc length formula. I can at least set it up from 0 to 2 pi, and then the square root of dr d theta squared plus r squared. I guess I don't have time, but use the formula that we derived on the previous page to finish that. So that's all for today, I guess.